Well, good afternoon, everyone. It really is a pleasure to be here. I've only been in Thailand for a few days, but I'm already in love with the country, and I'm very impressed with this university, what I've seen so far. I'm not going to talk directly about peace, but rather about revolutions. but rather peaceful revolutions. In fact, I'm going to talk about the coming revolutions in fundamental physics. The area of physics that I work in that tries to understand the basic structure of matter, the forces that act at the heart of the atom and the nucleus and even lower down. In other words, the field of physics that asks, what's it all about? Is it possible to turn the lights down a bit? Can you? It looks a bit faint. So what I'm going to really talk about are two things. First of all, the state of particle physics, of elementary particle physics, the physics of the elementary constituents of matter and the basic forces of nature. And then I will tell you something, the first revolution that many of us anticipate, that will occur very shortly, and will be based on new discoveries that we expect at a big particle accelerator, a kind of microscope that we are finishing in Geneva at the European National Laboratory, called the Large Hadron Collider, or the LHC. But mostly, I will be talking about why and what and where is a strange theory called string theory. Based on the idea, as far as we understand it so far, that all the particles, the fundamental particles of nature, are simply different vibrational modes, different ways that a single fundamental superstring can vibrate. This is a very ambitious theory, which has been around now for maybe 40 years, and we're still in the middle of trying to understand what the theory is and what does it predict. And I will discuss the revolutions, conceptual revolutions that I believe might be necessary to complete this task. But let me start with a brief survey of the present, where we stand today in our understanding of fundamental physics. We actually have a very successful theory of elementary particles. The development of this theory of the basic constituents of matter has taken perhaps 2,000 years to complete, starting with Democritus, who told us that everything is made out of atoms. That idea has turned out to be extraordinarily successful, for indeed, all of ordinary matter, the matter that we are made out of, that is around us in this room, can be understood. And we're understanding more and more about ordinary matter in terms of atoms. But atoms, as we learned in the beginning of the last century, have an intricate structure. They consist of electrons, the first of a family of fundamental particles called leptons, revolving around a point-like nucleus and governed by the laws of electricity and magnetism. The nucleus, however, is not a point-like particle, and as it was discovered in the last century, the nucleus itself is made out of neutrons and protons. But the neutrons and protons are not point-like particles, and as it was discovered the later half of the 20th century, they seem to be made out of point-like particles called quarks. And that's sort of the stage we're at now. We believe we have identified all the elementary particles, out of which all the matter that we see in this room and all the matter that we can produce in laboratories, some strange new kinds of particles, are all made out of up and down quarks, which make up the nuclei that we have, electrons and their partners, the neutrinos, and two other copies, or we call them families, of these leptons and quarks. But not only have we identified and measured the properties of the basic constituents of matter, we have actually understood at a much deeper level the forces that act on these particles and give rise to all the phenomena that we observe in nature. The force of electricity and magnetism that holds electrons in atoms and accounts for atomic physics and chemistry and presumably biology. But also the forces that act within the nucleus. That was the hardest thing to understand. The nucleus is a strange place and requires these enormous microscopes or accelerators to probe. That's the part that I was involved in understanding the strong nuclear force that holds quarks forever bound inside nuclei. There's another force in nature which we have understood at some level since Newton and later Einstein, and that's the force of gravity. These are the four forces that account for everything we have so far observed. So this is our theory of elementary particles, which is usually referred to as the standard model. Really should be called the standard theory. It is based on this identification of the basic particles, electrons, quarks, 2, 3 families of such particles, and the forces, which themselves are transmitted by particles. In the case of electromagnetism, it is the photon, the quanta of light. In the case of the weak force and the strong force, it's these particles, the so-called Z and W mesons, and the gluon of the strong nuclear force. This theory, this basic theory of matter and force, together with our understanding a la Einstein of gravity, the theory of general relativity, as far as we can tell, is the theory of all observed forces in nature. There are no phenomena that are not contained, we believe, that we have so far observed in this theory. And the theory is extremely well tested. We test this theory over large distances and down to microscopic distances of order a billionth of a centimeter. My friends who do nanoscience are proud to study nanometer physics, but we study physics down to nano centimeter. And there we test these fundamental theories with an accuracy which is sometimes unbelievable. In the case of our quantum theory of electricity and magnetism, we can measure certain properties. For example, the magnetic field produced by an electron, which is spinning. That magnetic field can be measured to 1 part in a billion, which means you measure a number and you have to worry about the 10th decimal point. Furthermore, theorists can calculate that number from first principles to 1 part in a billion and compare the two. And so far they agree, which tells us so far the theory is working. There's nothing new that must be put in. It is absolutely amazing that we have achieved such precision in science. The other components of the standard model are tested apart in 100,000, and in the case of the strong nuclear force, the hardest case, often to 1 part in 1,000. So this is an extremely well-tested theory down to the shortest distances that we can measure, and we see no reason why the theory has to fail anywhere except when we get down to very short distances. A distance length that will come up again of 10 to the minus 33 centimeters. That's nano, 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 lots of nanos. This is a remarkable achievement of mankind, of science, of physics over 2 centuries, culminating in this theory that works perhaps from the Planck length to the edge of the universe. The same theory is used to explain the behavior, the structure of stars, of galaxies, indeed, with gravity of the cosmology, of the structure of the universe as a whole. So we have this extremely powerful theory, works, incredible accuracy over 60 orders of magnitude. What a great achievement of physics. So should we stop and go home? Well, of course not. And the reason is we have so many questions. I like to say that, why do we do science? We do science to gain knowledge, to control nature, to understand nature. But I like to say that the most important product of knowledge is ignorance. Now, there are 2 kinds of ignorance. There is stupid ignorance, the kind of ignorance that underlies bigotry, hatred, but there's also the kind of informed and intelligent ignorance that arises from knowledge. In fact, ignorance is our greatest resource, because it's ignorance that propels us forward, that pushes science forward. It is good questions, and to ask good questions, you have to know a lot. The questions that were asked when I was a graduate student in physics, how does the nucleus work, etc., etc., wonderful questions, many of which have been answered, are nothing compared to the wonderful questions we ask today. Because we know more, so we can ask questions. Those questions couldn't have been asked and weren't asked 30, 40 years ago. We didn't know enough to be intelligently ignorant. So let's talk about some of the questions. For example, the world seems to be, the physical world, to be built, in addition to gravity, on these 3 forces, which all we understand come about, have their origin in some beautiful symmetry of nature. Why is that? We can imagine lots of other kinds of forces, but they don't occur in nature. Why? And then these different forces are characterized by different strengths. Some are very weak, some are strong. That's why it's called the strong, weak forces in the nucleus. This is a number that characterizes how strong electricity is. And the fact that 1 over 137 is sort of a small number compared to 1 means the electricity is weak. But why this specific number? Can we calculate this number? And then we have all of these quarks and leptons whose properties we've measured, but we don't understand why they have these strange patterns of masses, no understanding, and we don't believe that our framework at the moment, the standard model, can answer these kinds of questions. And then we were beginning, as we are pushed to include gravity in the game, the dynamical theory of space and time, to ask questions about space and time, such as, is space three-dimensional? Are there only three dimensions, left, that way, and that way to space, or perhaps more? Why? There are hundreds of such why questions that we ask today because of the very success of our standard model. And of course, we would like to know the answer to these questions to satisfy our curiosity. That is the driving force of science. But also, there are other sciences, and especially cosmology, that require that we understand the answer to these questions. In the last century, towards the end of the last century, we've learned an enormous amount about the fundamental particles and forces of nature, but we've also learned an incredible amount about the history of the universe. And the two are closely tied together. In this picture, we see a scheme of the history of the universe, which we now believe began in something we call the Big Bang. The universe then inflated, expanded extremely rapidly, and then settled down to what is a more or less constant rate of expansion. And we understand just about 99.9999% of that history based on observation. We can look back, in fact, 13.5 billion years ago and see the light that emerged from the hot soup plasma of radiation and electrons and nuclei that the universe found itself. Atoms formed, the light could escape, and here it is. This is the famous map of the universe 13.5 billion years ago, showing slight variations of density and pressure, which are exaggerated in this picture of different colors by about a factor of 100,000. The universe was extremely smooth at that point. These little clumps are eventually what grew into galaxies. And we can actually follow that, how galaxies form from those little fluctuations of matter 13.5 billion years ago, and understand the formation of structure that led to planets, stars, galaxies, planets, and us. But what we don't understand is what happened at and close to the Big Bang. And there we have no doubt that the physics that we have today is insufficient. It's remarkable that we know enough physics to extrapolate already back to a millionth of a millionth of a millionth of a second after the Big Bang, because the physics then was quite different, but we understand it. Quarks and gluons were flying around freely. They hadn't yet formed nuclei. But that we understand. But if we push back far enough, all of our equations break down. And so cosmologists really would like to know, are driven to know, and we too, how did it all begin? What was the Big Bang, and what was it like right after the Big Bang? That's what eventually produced those little variations in density that gave rise to structure, to us. Well, one way of trying to go beyond what we know to answer these why questions, to get further down to the core of understanding of nature, is to look for further unification. That's a method that has worked very well over the last 2 centuries, where we unified electricity and magnetism, and, for example, and are along the way to unifying the other subatomic forces. And in fact, that search has been greatly helped by the Standard Model, because the various components of the Standard Model, the three forces and the two kinds of matter, quarks and leptons like the electron neutrino, aren't just arbitrary pieces of some kind of puzzle. They fit together beautifully, as if all the forces came from a common origin and all the matter came from the same common origin, as if there was only one force and one form of unified force and matter. The various pieces fit together in a way that it is unavoidable to reach the conclusion that they must somehow be unified if we were to look at even shorter distances corresponding to higher and higher energies. But there is a mystery that this immediately raises, because the forces of nature look very different. And in particular, they have very different strengths. Electromagnetism, which is responsible for chemistry, atomic forces, is a very weak force compared with a strong nuclear force. That's why hydrogen bombs are so much which depend on the nuclear force, are so much more powerful than TNT, which is based on atomic forces, chemistry. So how can electricity and the strong nuclear force be different parts of the same force? How could they have the same strength, for example? Well, the resolution of that is one that was at the heart of my research, so I'll tell you a bit about it. It turns out, as we learned, the strength of forces can change as we change the distance of the phenomena we observe, or the energy at which these particles interact. So this turned out to be the secret of the nuclear force, that quarks interact very weakly at short distances, very strongly at large distances. And why is that? That's pretty strange. And that has to do with one of the deep lessons of quantum field theory, our current framework of theoretical physics, the quantum theory of fields. Fields like the electric and magnetic fields that give rise to electricity and magnetism. That has to do with the property of the vacuum. Now, most of you who are not quantum physicists, if you think of the vacuum, this is your picture of the vacuum, a pretty boring place. You take everything in this room and remove it, all the people, all the chairs, all the air, everything. You're left with a perfect vacuum. Cool it down to absolute zero. What does it look like? Well, this is your picture of the vacuum. Nothing. Perfect state of nirvana. Well, this is wrong. In quantum mechanics, you can't have a state like this. A fundamental principle we learned almost 100 years ago is that it cannot be the case. And essentially, it's Heisenberg's uncertainty principle. Assume that the vacuum is empty of everything. It's just quiescent. Well, let's check that, observe that, by measuring the vacuum. We send in a probe to determine what the state of the vacuum is, but then we disturb it. You know, in quantum mechanics, if you have a pendulum, the lowest energy state, the vacuum state, would be the pendulum at rest. But if you observe it, you start it moving. It makes no sense to say that it's not moving, because any observation will make it move. That's the uncertainty principle. There is always what we call in quantum mechanics a zero-point motion. Well, the vacuum space is filled with fields. And you might think they're just quiescent, so the vacuum looks like this, but no. If you observe them, they'll start fluctuating. So this is the classical vacuum is empty, but this is the correct picture of the quantum vacuum. And I know it's the correct picture because we can calculate what the vacuum looks like using our theory. Quantum chromodynamics, in fact, the theory of the nuclear force, which is the biggest effect at these distances. This is about the size of a proton. So on this scale, the vacuum is in fact full of chromodynamic fields which are fluctuating. Zero-point motion. The vacuum is a very complicated space. And in such a complicated medium, in fact, like like water, the forces can change with distance. You can have an up and down quark which exhibit at short distances weak forces, as they do. And when you try to pull them apart, the force becomes very strong. That was the realization that led us to a theory that could explain this phenomena, and this turns out to be the correct theory of the nuclear force. It's because that force, in the case of quantum chromodynamics, becomes strong, you can't pull these quarks out of the nucleon. Here is a picture of a nucleon, a proton. It's made out of 3 quarks, you see. And let's try to pull them out. Well, you pull, and this very strong force field develops in between, which prevents you from doing that. So they bounce back. This is the phenomena called asymptotic freedom, in fact. The fact that the strong force, the strong nuclear force, gets weaker as we go to shorter distances, which corresponds to higher energies. You need higher energies, higher frequency light or particles to probe shorter distances. So large distances is low energy, short distances is high energy. The force decreases as a function of energy. This is unusual, in fact. Electricity and magnetism increase with energy. The electric force gets bigger if you go to short distances or high energy. And therein lies perhaps the resolution to how could you unite the strong force and the electric magnetic force. In fact, today we do observations up to this energy scale, and we can see that the strong force is getting weaker and the electromagnetic force is getting stronger. And although we can't do observations at these very high energies yet, we don't have the accelerators, we can use our theory to extrapolate. And people did this shortly after the Standard Model was completed, and extrapolated using theory the 3 forces to very high energies, and this is what happens. The 3 forces come together as if they are indeed unified and emerge from a unified theory that works, that holds at very high energies or short distances. This is a logarithmic scale, so this is 15 orders of magnitude higher energy. In fact, this was the first sign that unification occurs at very short distances. And at first sight is very depressing, very bad news. Because it is very hard to do experiments, maybe impossible. Who knows? Certainly today we can't directly probe these very high energies. So why am I excited about the LHC, which is going to turn on and maybe take us to this energy. It's not going to directly probe unification. The reason is that we expect new physics, not unification directly, but something very exciting to occur at the LHC, and that is a new symmetry of nature called supersymmetry. And since this is going to be, I hope and expect, discovered very shortly, I want you to understand it so that in a few years, when you learn that supersymmetry is discovered, you'll know what that means. Symmetries of nature have been, we've understood, are essential. Nature loves symmetry. Nature loves beauty. And symmetries are part of our understanding of beauty. The way we say, describe symmetry, the best way to describe the symmetries of nature is as transformations of some kind of space. For example, one of the symmetries of nature is rotational symmetry. The principle says that the laws of physics are unchanged under rotations. What does that mean? It means if I do an experiment, here's an experiment. I drop this, I measure how long it takes to fall. Now I rotate the laboratory. I do the same experiment, measure, get the same result, right? That's rotational invariance of the laws of physics. We have another very important symmetry of nature called translational invariance. I do my experiment here, I go across the room, I do the experiment, I get the same result. That's very important. I don't know how we would survive without that symmetry of nature, because we would have to say, well, I did an experiment in Berkeley and I got one result. I did an experiment in San Francisco, I got the same, different result. It would be awful. Symmetries are very important. Supersymmetry is a wonderful extension of our ordinary notion of the symmetries of space-time, like rotations of space. The easiest way to describe rotations is I rotate space. Right? I rotate the x-axis into the y-axis. So, the best way to describe supersymmetry is to describe superspace, the space in which these transformations act. So superspace is a generalization of space. Space, of course, is, x, y, and z. That's where how you measure the location of particles, and time, of course. Superspace has new dimensions, new coordinates that you can move in, which I call here theta. And the reason I use the Greek alphabet is because these new coordinates, these new dimensions of space are kind of strange dimensions. We measure them not with ordinary numbers, but strange numbers that anti-commute, whose multiplication law is not commutative. So here we measure, I walk 2 meters in this direction or in this direction, and 2 is an ordinary number. 2 times 3 is equal to 3 times 2. But when I walk in the theta direction, I measure in numbers, theta 1 and theta 2, where theta 1 times theta 2 is minus theta 2 times theta 1. Well, that's a pretty strange kind of number. But, mathematicians invent all sorts of strange numbers. We've heard of the square root of -1, imaginary numbers. These numbers aren't even as weird as that. And turns out there's a beautiful generalization of ordinary space and time, which include extra dimensions, which you measure using these sort of quantum dimensions. Quantum because they don't commute. And superspace is just that. It's a space that contains sort of, for every ordinary dimension, a new quantum dimension. And because of that, it turns out that theories of physics, you can take any theory you want of physics and that's formulated in space and formulated in superspace, And it has many beautiful properties, but one of the consequences is that if for every particle that you had described in ordinary space, in superspace there has to be a new kind of particle that you get by sort of rotating these ordinary dimensions into these new quantum dimensions. So people sort of discovered supersymmetry a long time ago, actually in string theory. And it was kind of a beautiful structure. The first implication, however, seemed pretty bad because every particle that you ever discovered in nature had to have another particle. And we gave them strange names. The quark, there had to be another particle called a superquark, a squark. And the electron, a superelectron, a selectron, and a photon, for the quanta of force, like the photon, you add eno, so the photon has to be accompanied by a photino. None of these particles have been observed. You might say, well, that's pretty bad. You throw out that theory, it doesn't work. But that's not the case because we understand, in fact, one of the great lessons of the 20th century was that there could be new symmetries, like supersymmetry, that are symmetries of the laws of nature, but not apparent in the world that we see. And here's an example of such a symmetry that you know about. It's called rotational symmetry. The laws of nature, as I said, don't change if you rotate the laboratory. The laws of nature are rotationally invariant. But this room is not rotationally invariant, right? You're there, I rotate, I can't see you. So this room is not, well, you say this room is a complicated space. Take out everything from the room. Everything. You're left with a vacuum. The vacuum is this simple white sheet, which is rotationally invariant. You can rotate a white sheet of paper, it doesn't change. But remember, the vacuum is a complicated space. It's a complicated dynamical medium. It, in fact, can look like this room and not be rotationally invariant. That's a big lesson we've learned. And, in fact, we have discovered symmetries of nature that are symmetries, exact symmetries of the laws of nature, but not of the vacuum, not of the state of the world that we live in. So, if that's the case, if supersymmetry, we say, is spontaneously broken, then these particles could be very heavy. And there are reasons to believe that they would appear just at the right energies that we would see at the LHC. And the hints that we have to do with, for example, this unification. As years went on and people measured better and better the forces. So these on a logarithmic scale are the inverse strengths of the three forces. And therefore could extrapolate better. The theory got better. Do better calculations. The extrapolation turned out not to work, from which you might conclude there is no unification in the standard model. But then people said, well, what about these, if we make the standard model supersymmetric? And then it works beautifully. And by now, with great precision, this is agreement when you extrapolate the standard model, supersymmetric version of the standard model, to about 1 part in 1,000 when extrapolated over 14 orders of magnitude. If supersymmetry is there. It also, supersymmetry helps us explain other things, the reason the unification scale is so high. But most interesting, it explains something that was not even known when supersymmetry was invented, dark matter. As you must have heard, the astronomers have concluded that 90% of the matter in the universe is some kind of heavy particle that we can't see, but stars can feel. So when astronomers look at a galaxy like our Milky Way out there in the universe, and they measure the orbits and velocities of stars in that galaxy, they can calculate how much mass there is that holds the stars in place, and they discovered that 90% of the mass is not visible. If you just add up the mass of all the stars in the galaxy, it's not enough. It's only 10% of what you need. So the rest, they conclude, must be, as pictured here, the blue stuff, in the form of some very heavy particle that interact very weakly, so it doesn't clump together to form stars, does not radiate light, so we don't see it, but is there, and we can measure its properties through its gravitational effects. What is it? Well, remarkably, the supersymmetric theories say that there will always be a lightest partner, super partner, that will be very heavy, and if it's just at the right mass, around 100 GeV, billion electron volts, so roughly 100 times heavier than a proton, it will account for 90% of the matter in the universe. So this is the reason we're, at least I'm very excited about the LHC, this large accelerator being built in Geneva. You know, it goes between Switzerland and France. The protons zoom around this 20-mile ring at this almost the speed of light, passing from Switzerland to France millions of times every second without going through customs. And they smash together at places where these immense detectors are being built to detect the products of the collisions of these protons and figure out what's going on and whether one has produced a dark matter particle and discovered supersymmetry. So this collider could discover the super world, and in a few years from now, when you open your newspaper or internet and read that scientists at CERN have announced the discovery of supersymmetry, I want you to remember that that is tantamount to the discovery of quantum dimensions of space-time. It will really mean that we live in a world in which, in addition to ordinary dimensions, have quantum dimensions, and the laws of physics are invariant under transformations of that super space. That, in my mind, would be quite a revolution of our understanding of space and time. But that doesn't take us to the unification scale. Here we have, however, luckily, another important clue, and that is the fourth force, which isn't on this list because it's so weak at low energies. Gravity. Gravity is a very weak force. I find some people find that hard to understand because it's the only force they feel. They get up in the morning, get out of bed, they feel gravity. Why is that? It's the weakest force in the universe. In the atom, gravity is 10 to the 40 times weaker than electricity. But it's the only force you feel because the other forces are so strong that they immediately get neutralized. The atom is a neutral object because the electrons are pulled very strongly to the nuclei and the whole atom is neutral, so it doesn't exert much of a force anymore. But gravity is not neutralized, and if you put a lot of matter together, it together pulls rather strongly, as we feel. But still, it's kind of weak. And here's the proof. Hold up this, I'm holding up this little laser pointer. Now, that's not remarkable. You hold up things all the time, right? But you've never thought about it. What you're doing is exerting a little bit of chemical force through your muscles, right? And that comes essentially from electricity, from chemical reactions that are occurring in the muscles. So this is a little bit of electrical energy. You are opposing, the whole Earth is pulling on this. So on the one side you have the whole Earth pulling this down, and you're holding it up with a little bit of electrical force. Gravity is very weak. You have to put together a whole planet to get any noticeable force. But gravity the force of gravity, as you know, is mass. Gravity is the force between mass. And the one equation that I'll use here is E equals mc squared. Einstein taught us that mass is just the energy of an object at rest. So gravity really, the charge of gravity is energy. Gravity is the force between two objects that have some energy. If they're slowly moving, it's mostly their mass. So gravity is proportional to mass or energy squared. And therefore, as the energy goes up, if you have two particles moving very fast with respect to one another, the force of gravity will go up quadratically with their energy. So as you go up in energy, gravity increases quadratically. These other forces are getting smaller, like the strong nuclear force, but logarithmically. So if you go up 20 orders of magnitude, gravity will be 40 orders of magnitude bigger and comparable to the other forces. And where that happens, remarkably, is at the same place. That's a very strong hint that the next unification that we're driven to of the three forces that act within the atom and the nucleus will be together with gravity. And that's what brings us to string theory. And the reason is that quantum gravity, understanding gravity in the regime where it's strong, means understanding the quantum effects of gravity, which we can forget about unless gravity becomes strong. And our framework of quantum field theory doesn't seem to be able to deal with it. Remember, I told you the vacuum is this complicated place because everything in quantum mechanics is fluctuating. Well, Einstein taught us that gravity is the dynamics of space-time. Mass or energy curves space and time. That's what gives rise to the distorted motion of objects we call gravity. So gravity makes space-time dynamical. So what is fluctuating is space and time itself, and that causes problems. And within the framework of quantum field theory, of Einstein's theory, in fact, these fluctuations of space-time at these short distances where gravity is strong become uncontrollable. People talk about space-time foam as if the very structure of space is so violently fluctuating that space loses its meaning. Perhaps it does, but within the framework of quantum field theory, we just can't control it. And string theory can. It does seem that Einstein's theory breaks down. String theory is an example, the only one we know which goes beyond it at these very short distances, replaces it by something better, smoother, less violent, and yet reduces to Einstein's theory at larger distances where gravity is weaker. It says that if we look very closely at a quark or a lepton or an electron, we'll just see that they're different vibrational modes of a single string-like object. And not only the electrons and the quarks, but the quanta of force, the photon, the graviton, will all be different harmonics of the same string. That is a bit of a break, at least with historical tradition, of basing our fundamental theories on fundamental particles. But it's not that much of a break with the past. I like to say that string theory, so far, is a rather conservative modification, or a conservatively radical modification of the principles of physics. We replace particles by strings, but we keep all the other principles of physics unchanged. Now, it is very difficult and very rare to change the basic conceptual framework of physics. Of course, I get manuscripts on my desk and emails nowadays, many every week, changing the fundamental principles of physics. But they're all obviously wrong, in contradiction with experiment or logic, or usually both. It is very difficult and dangerous to tamper with the fundamental principles of physics. If you're going to do so, and this applies not just to physics, but in my opinion, to social phenomena as well, you should make one change and keep the rest unchanged, fixed. Much safer. And that's what string theory sort of has done. We've changed this basic principle that we base physics on point-like objects, but we don't change any of the other principles. And in doing so, people have constructed string theory following that strategy, and remarkable things have emerged. But how we do this is really following these rules. We know how to describe particles. Particles move along trajectories. And we have all sorts of techniques to deduce the laws of motion of particles. And we can just take those over to describe strings, which move along tubes. So you just take all the equations, or at least all the approaches to physics that we've perfected over the last 100 years, replace particle by string, this line or trajectory by a tube, the length by the area, and so on and so on. The mathematics gets a bit more complicated, but conceptually, string theory is not that crazy or radical or new even. It's just that we consider the motion of strings instead of that of particles. We can do that classically, we can do it quantum mechanically. Remarkably, however, when you come to discuss the forces between particle strings, one new thing has emerged of immense significance. One of the ways we describe the forces between particles is to say that the way particles interact is by means of these kinds of diagrams. They're called Fineman diagrams. Feynman developed this picturesque way of doing quantum mechanics of particles. Particle A and particle B come together, are at the same point at the same time, this interaction point. They can turn into particle C. For example, an electron and a positron, when they come together, can turn into a quanta of light, a photon. And that is a way of actually describing the forces between particles. And all of the action occurs at this point. This is the place you have to say, okay, this is what can happen. A and B can turn into C. There's some probability for that to happen. That's a number that you have to put into the theory. In fact, all of the numbers we can't calculate, the parameters of the standard model, come into specifying what happens at these vertices of these graphs, these Feynman graphs. And you can try to generalize this picture to two strings coming together and turning into a string. You know, an electron string and a positron string have to turn into a photon string. But there are two different ways of doing that, remarkably. So here's string A and string B, and they could come together, and when they're on top of each other, turn into string C. That leads to a sort of a picture like this. So this is taking that old picture graph and blowing up the lines into tubes, and when the tubes overlap, they turn into a third string. Well, this is, if people had followed this course, which they didn't, not because they knew better, they just, how things developed, it would have been disastrous. But there's a, so that was the bad way. This is a good way. String A and B, again, come together, and they move along, and they kiss each other, just hug. And they turn into a third string. much milder, softer type of interaction. This works beautifully. It gives not the picture I drew before, but what's called the pants diagram. So this picture has them overlapping completely, and if followed, would have led to a very sick theory, and one where one would have had to specify a number for each of these interaction curves, an infinite number of arbitrary parameters. But this pants diagram, because it looks, this is a picture of two strings coming together, forming a third string, looks like pants. So they call it the pants diagram. And you see, if you start with a trouser, you have one string, and you take slices, you have two strings, two legs, and they end up being the belt, which is string C. And you know, if the pants are well made, you can't really tell where this interaction took place. More precisely, if you're an ant walking on that diagram before, which had a vertex, you know where the interaction happened. There's one point where three lines come out of it. But if you're an ant walking on very well-tailored pants, every area looks like every other area. There's no place where the interaction takes place. In fact, the string interaction is topological. You can't really, once you know how strings move freely, you also know how to construct the interaction. This is the most remarkable feature of string theory, which whose significance and real deep meaning we don't truly understand. But it is a fact that in string theory, unlike any other theory of physics before, we can't change it. You can't dial parameters or interactions. There are no parameters in the theory that are not dynamical. There are no numbers that you can choose. They're all, in a sense, dynamical. In that sense, string theory seems to be a very unique theory. You can't change it. It's not like a model where one tries to construct a model of some phenomena, and if it doesn't work, you change some parameters, or you add some new features. String theory, as we've discovered, and we don't really know what it is yet, as I'll explain, whatever it is, we can't change it. We're stuck with whatever it is, and we explore its properties. There's only one consistent way of constructing whatever it is we're constructing. And in doing that, being led down this road with little choice, one discovered amazing properties, most of which originally people did not want, because they were originally trying to construct not a theory of all the forces in gravity, but a theory of nuclear particles and forces. And now, today, we understand why they were led to string theory, because when you take a quark and an antiquark and separate them, as I told you before, this force field develops between them. This flux of the chromodynamic field forms a flux tube, a kind of fat string, which looks in many ways like a string. In fact, today we understand from quantum chromodynamics why a string picture works so well, and are trying to develop the dynamics of the QCD string that could describe these particles. So this fat string, this is a real calculation using quantum chromodynamics of what happens when you pull apart a quark and an antiquark. That fat string is what led people to string theory. And in the solutions that were constructed to string theory originally, all sorts of things emerged that initially people didn't want, but now are regarded as, well, some of them as good things. For example, one of the things that originally was bad, now we live with, is that there are more dimensions in space and time. 26 originally. And then it was discovered that if you want to explain particles that were spinning, you had to have this supersymmetry. That's how this new symmetry of space that might be there was originally discovered. And then Space-time only needed 10 dimensions, but that still was too much for the nuclear world. And then the local symmetries, like the symmetries that underlie the Standard Model, appeared automatically. And then gravity appeared automatically, which had no place inside the nuclear distances, and much more. So this has been the history of string theory. One, without being able to dial or change the theory, we have been sort of almost like experimental physicists discovering its properties. What can we say we have achieved in these many years of exploration? Well, in some sense, we have an extension of the conceptual framework of physics. We have, for the first time, a theory of fundamental physics, which contains all of the kinds of forces we've described so far, and all the kinds of particles we've described so far, but is based on extended objects, strings, and not particles. Is this a revolution? We've had two revolutions in the 20th century in physics, deep revolutions. One was relativity, special and general, and one was quantum mechanics. They are actually connected to two of the fundamental constants, dimensionful constants of nature, the speed of light, Planck's quantum of action. Some of us believe that string theory, or what string theory will eventually turn out to be, is the third and connected with the other fundamental dimensionful parameter of nature, Newton's constant of gravity, which is a dimension of length, this very small distance. But this revolution hasn't yet really occurred. String theory hasn't yet broken at a conceptual level with, in the way that relativity and quantum mechanics broke with classical theory. The second achievement is that string theory has provided us with a consistent theory of gravity, of quantum gravity. And the third is that it provides us with this extremely rich structure that seems to have everything we need to construct the Standard Model. This is where people start talking about a theory of everything. String theory seems to have all the ingredients we need. So let me briefly discuss these achievements. The one that is undeniable is that we have an example of a quantum theory of gravity, thereby disproving the suspicion of many that there was something inconsistent between general relativity, Einstein's theory of gravity, dynamical space-time, and quantum mechanics. For years, people were trying to marry the two, and many had concluded that one would have to give. People doing general relativity usually assumed that it would be quantum mechanics. People like me, coming from particle physics, assumed that it would be Einstein's theory, would only be an effective theory, and that's what string theory says. More interesting, now that we have a consistent theory of quantum gravity, we can explore some very fascinating paradoxes. For example, the fate of black holes. You know, black holes are these strange objects that are predicted by Einstein's theory. If you get enough mass together, you form an object which is so dense, the gravity is so strong that even light can't escape from it, so it looks black. Black holes originally were thought by Einstein to be crazy things that were bad, just silly solutions of his equations, but later taken seriously and now observed all over the universe. It seems now to be a fact that in the center of every galaxy there's a massive black hole. In the center of our galaxy we have observed and measured the mass of a black hole which weighs as much as 1,000,000 suns. How do we know that? Well, we can't see the black hole, but we can see stars going around something whose mass must be 1,000,000 suns. So we think it's a black hole, and in other galaxies there are even bigger black holes seem to be playing an important role in the evolution of the universe. But for theoretical physicists, there are even more marvelous laboratories for our ideas about strong gravity. And Stephen Hawking was worried about the following phenomena. You know, if you throw stuff into a black hole, classically it never gets out. Nothing can get out. But quantum mechanically, he discovered black holes will radiate. This is due to quantum effects, not allowed classically, but happens quantum mechanically. But what comes out is disordered thermal radiation. It's as if you have all of this information you put into the black hole, and what comes out is totally informationless. You lose information. Well, in fundamental physics, one of the fundamental principles of quantum mechanics is you don't lose information, which is awfully good. Information is preserved. Oops. So, Hawking said, if black hole evaporation loses information, then the laws of quantum mechanics are violated. And so what probably happens, according to Hawking, was you have to change quantum mechanics. Well, string theorists, you know, people who came from particle physics didn't like this, and in fact, string theory saves the day. We now have a much better quantum theory of gravity where we can treat this process and prove that information is not lost. So much so that even Stephen Hawking has agreed that he was wrong and information is not lost. So that's a great achievement. We hope for even better achievements, because now we can begin to ask questions like, well, what does happen at the Big Bang? Previously, all of our equations broke down. Singularities developed in Einstein's equations. So can we start asking and maybe answering, what is the origin of the universe? Can we understand that? That's a new kind of question, very difficult. Well, unfortunately, the answer is not yet. Oops. The answer is not yet. All of this is good, but string theory suggests something else. It actually suggests that the framework we have been using of space and time is going to have to be radically modified. I'll come to that in a moment. But what about this theory of everything, this unified theory? It's true that simple so-called solutions, or consistent solutions of string theory, and there are many, seem to can produce the particles and forces of the standard model that we need. But truly finding a realistic description of the real world, the standard model, requires very difficult dynamical problems to be solved. The easy physics we could predict using string theory is the physics of what happens at these exceedingly high energies. But we can't do experiments there. So we have to predict what happens at lower energies, where we can do experiments. And then we, for example, have to understand how the extra dimensions, what happens to those extra dimensions of space. And how does this symmetry, supersymmetry, which underlies string theory so much, get broken? And then we have the problem of the cosmological constant, or the vacuum energy. So these are all difficult problems, and they really have made it difficult for us to make calculations of what the low energy world should look like. The extra dimensions, the problem of extra dimensions can easily be solved in many ways, it turns out. One way is that these extra dimensions of space are curled up into little curled up geometries. And this is a picture of one of the geometries called a Calabi-Yau manifold, in which 6 extra dimensions are curled up into a rather beautiful space, which is projected here onto the two-dimensional plane, or the Calabi-Yau manifold. And when you can find solutions, systematic solutions of string theory on such spaces, so we have the usual 3 big dimensions, and then the extra dimensions are all curled up, beautiful spaces, solve the equations for these spaces, and then you look at what you get out, and remarkably, the nature of the forces, the kinds of forces you would see in such a world, and the form of matter, what kind of matter you get, and the things we can't calculate normally, like the values of the masses, are actually all determined by the geometry of this hidden dimension, these hidden dimensions. This is, I think, a wonderfully beautiful way of answering some of those why questions. Why are the masses of the quarks and leptons so different? Well, it's because of the geometry of this internal space. This is an answer the Greeks would have loved. One of the big problems, however, in any of these attempts to find a solution of string theory that looks like the real world is the vacuum energy. Remember, the vacuum is this complicated space full of fluctuating fields, and all of that motion gives rise to an incredible energy present in the vacuum. Naively, that energy is enormous if you just use back-of-the-envelope calculations. And for years, people were worried about this, but since it was so big, and actually before string theory it comes out to be infinite, they said, well, since it's so big or so infinite, it must be 0. It's a very common reaction of physicists if something doesn't work by this. You see, to agree with observation, it would have to be 120 orders of magnitude smaller. One of the attractions of supersymmetry was that it said, well, it is 0. But then supersymmetry had to be broken, so it's still much bigger than it could be. And when recently astronomers claimed that the universe has an accelerated expansion, which is the effect that such a vacuum energy would give, Einstein's cosmological constant, at this order of magnitude, this became a severe problem for us. How can we explain that vacuum energy? And how can we come up with one of the solutions to string theory which would naturally give something like this? This remains the biggest conceptual problem for theoretical physics, in my opinion. Certainly for string theory, how to explain the dark energy that has been discovered in the universe. And this is a problem in string theory. In fact, it is a problem so severe that it has driven some of my otherwise sane colleagues to extreme points of view. They say that, and this is true, it seems that in constructing so-called solutions of string theory, there are zillions of them. There's only one theory, it seems, but zillions of solutions. Very strange. And as far as we know, they're all equally good or equally bad. But at the level that we understand, they're all equally good. And they say, well, you know, it might be because of ideas like eternal inflation or whatever. The universe began and could have ended up in many different solutions. Or the universe is very big and there are different portions, each of which came from a different region, a different solution, so that one can imagine that the universe is actually immense. And one pocket of it is in universe A, solution A. And in that pocket, this vacuum energy is so big, or normal size actually, that the universe expands so rapidly that galaxies would never have formed. And so life would never have been there because there would be no stars and no planets. So obviously we're not in that portion of the universe. In fact, the range of this vacuum energy which would have enough time for galaxies and stars to form is very small, so we're only in that kind of solution or portion of the multiverse in which life could form. So don't calculate the cosmological constant. You can't. It is what it is, because if it wasn't, you wouldn't be here to ask the question. This is known as the anthropic principle. And I am well known as a vicious opponent of this approach to science. And I truly think, for the time being, it is better to follow Einstein's law that theories should be so strong that they could, in principle, eventually explain everything. There shouldn't be any arbitrary parameters, even ones that are chosen because we're here to ask the question. And I don't think we're ready to come to such conclusions, and we're unfortunately not ready to make real predictions or calculations yet at low energies, because we don't really understand what string theory is. I sort of explained to you how we construct string theory, but not what it is. There's so many different ways that we have now of looking at string theory, like the elephant being felt by the blind men. But what is at the heart of the theory, we don't know. Remember, it began as a very modest modification of the principles of physics. But these strange things happened, came out of the theory. I'm now running on reserve power. And we've discovered that maybe thinking about string theory as strings moving in space-time is not the right description of string theory. We have other descriptions which are equally valid. For example, the same theories we use for the standard model, QCD or theories very close to it, very similar but more supersymmetric, are equivalent to string theory. We, in fact, have discovered dozens and dozens of ways of describing string theory. Some of them start by strings moving along. Some of them don't have strings at all. Some of them don't even have space. Some of them don't have gravity. But they're equally mathematically equivalent ways of describing the theory. Very powerful tools, these dualities, these different descriptions of the same theory, but we don't know what the theory is, and we certainly don't know what will come next, what the next surprise will be. I think it has to do with the nature of space and time. And I'll end by describing what I think is the next big conceptual revolution in fundamental physics, which has to do with the fact that some of us believe, as Edwin said, space and time may be doomed, or space and time are illusions. Now that sounds perhaps a little scary. Now what does it mean? Well, we have learned, we've been forced to think in quantum gravity, and especially in string theory, about the very nature of what is space and time. We've already, Einstein forced us to modify our notions of space and time, but we still have space and time around, but maybe not for long. Some people used to think that, well, what really happens is at the very microscopic level, space and time is very rough, space-time foam. But what I think we're being led to in string theory is that space, especially, is an emergent concept. It really isn't fundamental. And we already have examples, many examples, where our best description of string theory is in a description in which some or all of space is not there. We have descriptions in which some or all of space emerges as an approximate way of describing large-scale phenomena. But at the fundamental level, space never enters into the equations, into the description of the theory. And that suggests to us two things. First of all, that if we ever were to really understand string theory, what is it that we describe in so many different ways approximately, it would not have space as a fundamental concept. And if it doesn't have space in this relativistic era, presumably it wouldn't have time either. Space and time have already been unified by Einstein. And this is where I think we're really stuck, because we have no idea what it would mean to formulate physics in which the notion of time itself was emergent. Because physics is all about predicting the future, given the present, propagating information in time. How can you formulate, how can you get started with even the rules of physics if you don't have time as a primary concept? This is where I think we're stuck. One of the reasons we can't yet address questions like the cosmological singularity, the Big Bang, is because we don't know how to find the more fundamental formulation of physics in which both space and time are emergent. So, to summarize briefly, string theory has many hopes for the future. It has all the ingredients to unify the forces. It seems to suggest, however, that we will need new concepts of space and time. And that might help us resolve the remaining puzzles and paradoxes of quantum gravity, cosmology. These are difficult, difficult problems, and will require, certainly this one, revolutions, true revolutions, breaks in the way we think. And those are hard to predict. And luckily, string theory can do much else for us, it seems. It gives us new insights into the theories we already use to describe the standard model. It gives us incredible new insights into mathematics. It gives us new kinds of phenomena that we might observe, new phenomenological scenarios. And it might, in the end, come back to its origins and give us a new way of looking at the nuclear force. And there's a lot of progress being made on this recently. So we have a wonderful theory of elementary particles, but the most interesting questions remain to be answered. We have, luckily, new accelerators that are coming soon, and exciting discoveries, I think, are around the corner. And string theory has many successes, has much progress, and many problems, but the best is yet to come. Thank you.